In this exercise, I want to show you how useful it is to understand potential and conservative vector field. We will compute this line integral for this vector field over this curve in two ways. First, without any notion of conservative vector field and potential, just by direct substitution. And then we will consider the question whether this vector field has potential, whether it is conservative, and how can we make use of this fact. So let's start with the first stupid way. We have the vector field fxy having components y squared and 2xy, and we have the unit circle. X is cosine of t, y is sine of t. T runs from 0 to 2 pi, and we run around the circle once. We make one complete turn. So we prepare the derivatives or the differentials. Dx will be minus sine t dt, and dy will be cosine of t dt. And then the integral will be integral from 0 to 2 pi f1, which is y squared, which is sine squared, dx, which is minus sine t, so we have sine cube, plus f2. f2 is 2xy, so we have 2 cosine of t, sine of t, times dy, which is cosine of t, so we have cosine squared of t, times dt. To compute this integral, it's a good idea first to consider the antiderivative. So first let's consider the antiderivative without the limits. And it will be good, well yeah, we can factor out sine, and we have 2 cosine squared of t minus sine squared of t. We can express sine as 1 minus cosine squared of t, and we can use the substitution for cosine. Say u is cosine of t, and then u is minus sine of t dt. Then sine of t dt is up to the minus sign, the differential of the new integration variable t. And we have minus integral, and here we have 2 cosine square plus cosine square, which is 3 cosine square, and cosine is u, so we have 3u square. Minus 1 du. So this is integral 1 minus 3u squared du, which is u minus u cubed, and u is cosine, so we have cosine t minus cosine cube of t. And then the integral, the definite integral, will be this antiderivative evaluated at 0 and 2 pi. Cosine of t minus cosine cube of t. But independently of the value at 0, the value at 2 pi is the same because cosine is a periodic function with period 2 pi. So we subtract two equal values, which happen to be 0 in this case even, but the result is 0. Okay, that's That's the first approach to this integral. Once again, we have some curve, we have some parameterization, we have the given vector field, and we use the direct substitution, and we evaluate this integral by combining all these steps. And here's the result. Okay, finished. But now I will show you one way how to compute integral without integration. Differentiation will be enough. Because x and y at 0 x is 1, y is 0. And at 2 pi, again, x is 1, y is 0. So at the endpoints of the interval, the point of the curve is the same. The initial point coincides with the endpoint. Such a curve is called a closed curve. This is a dangerous term. Closed. We have seen closed in already 3 different situations. Closed interval, meaning the endpoints do belong to the set. Closed set, as a subset of Rn. A closed set is a set for which the complement is open. But here, when we say this curve is closed, which happens to be closed in R2, but this is a different meaning than a closed set in the sense that the complement is open. So not to be confused, the term closed is used in different meaning. But if the initial point of the curve is the same as the end point, we say the curve is closed. It may look like that. It may even cross itself. No problem. And say a triangle is an example of a closed curve, square or rectangle, circle is all these examples of closed curve. When we evaluate the line integral over a closed curve, we usually, we always hope the field is conservative. Because if the field is conservative, then the integral is equal to the difference of the potential at the endpoint minus in the initial point. And if the points are the same, then independently how difficult or easy the potential is to evaluate, the difference will be 0, exactly 0. Even in case we don't know the form of the potential. Just the existence of the potential is completely enough and we are happy. Well, and we have a condition, we have a signal that the vector field is conservative, that means it has potential. We consider the 2 components of the field, F1 being y squared and F2 being 2xy. And then we just compute nothing more than these 2 partial derivatives, first component with respect to the second variable, which happens to be 2y. And then the derivative of the second component with respect to the first variable x. And this is 2y. And if this is true in some open, simply connected set, which R2 is perfectly yes. If this is true in some open, simply connected set, then the vector field is conservative, it has potential, it is path independent, meaning the integral is path independent, and the line integral along a closed curve is equal to 0. So the second clever approach is, we just consider, or we just show or verify that the line is closed That means it goes back to the original point. And we compute these two partial derivatives. And we are done. If this is true, then the integral is definitely 0. Just from the fact that the field is conservative, that it has potential, we don't have to find the form of the potential. So we compute the integral only using differentiation, no integration.